Hello and welcome to Equity Education, the chemistry version, and today we're going to be looking at analytical techniques, and specifically we're going to be looking at infrared spectroscopy and mass spectrometry. So we'll have a look at these two analytical techniques and how we can identify organic molecules from them. Okay, so I'd like to go ahead and get started, so can you open your booklets and we'll start. So infrared spectroscopy. So infrared spectroscopy is used to identify functional groups of organic molecules or bonds in organic molecules. A beam of infrared radiation is passed through a sample of the molecule to be identified. Okay, so how does it work? Well, all bonds vibrate at a certain frequency. The frequency at which the bond vibrates depends on the two atoms in the bond. So when infrared radiation is passed through a bond, if that infrared radiation frequency corresponds to the frequency of the bond, then the bond absorbs this frequency of radiation, and this produces an infrared spectrum, as shown below, and we'll have a look at that in a minute. So what it basically means is that if we have two bonds, two atoms, they vibrate at a certain frequency. If you pass infrared radiation into it and it's at the same frequency, the bond will absorb that energy, and because that bond absorbs the energy, we will get this spectrum produced. Okay, so you see these things here going down, and we call them troughs, or we call them peaks. And the units for working out wave number are centimeters to the -1. Okay, so what are these things? So there are troughs on the infrared spectrum. These are known as peaks, which is a bit confusing since they're troughs. Or absorbance. The absorbance represents the particular frequency at which a bond is vibrating. Therefore, it can be used to identify bonds. Okay. E.g., if we just go back up here, so this here, this trough or this peak, is an absorbance of a particular bond, and I can look in a data booklet to figure out what particular type of bond this is. Okay, so moving on. So different functional groups can be identified on the spectrum by looking at the pattern. The three ones you will need to know for this unit are, well, when I say unit for this particular part, are first of all, alcohols. So my bond would be an OH. Aldehydes and ketones is a C double bond O, and carboxylic acid again would be an OH. Okay, so my wave number for an OH and an alcohol is around about 3,200 to 3,550. For a C double bond O, it's 1640 to about 1750. And OH in a carboxylic acid is 2,500 to round about 3,300. Characteristic of the peak or the absorbance, so it's broad, this peak. C double bond O is a sharp peak, so it's not that broad, but it goes down quite a lot. And for an OH and a carboxylic acid, it's very broad. Okay. So, moving on. So all organic molecules will have a peak at, this means about 2,800 centimeters to -1. This represents a carbon to hydrogen single bond. Nothing can be inferred from this. There are lots of other bonds that can be identified, but these will be given to you in a data booklet. So the above values that I've given will be given in a data booklet as well, but it's better just to remember them because these are what you're going to use to identify organic molecules. Okay, so identifying ethanol. So ethanol would look like this. What identifying absorption should be seen in ethanol? So before I go down, I want you to have a think about what you would see. Okay, I'm sure that you've worked out that we should see an absorbance at a wave number of between 3,200 and 3,550, and it should be pretty broad. So if we go down, this is my spectrum. And unsurprisingly, we see a broad absorbance here, which represents my OH group. So we see a broad peak at round about 3,300 centimeters to -1, which represents an OH. And you may also see these are my CH bonds, which you will see in all organic molecules, so we can't infer anything from these values. We'll talk about these in a little bit. Okay, so identification of a C double bond O. What specific absorption should we see of a C double bond O? Well, I don't think you need any time to do this. We can just write it down. So a sharp absorbance at about 1740 centimeters to the -1. Okay, we go down. This is my structure of ethanol. You will notice that there's no OH peak now because we don't have OH in the molecule. However, there is a sharp absorbance at about 1740, which represents my C double bond O. And here I have some more CH, which I can't infer anything from. Okay, so moving on. Can we identify from just infrared spectroscopy between an aldehyde ketone and an ester? Well, no, we can't. Because they will all have a sharp peak at about 1740 centimeters to the -1, as you probably know, because they contain a C double bond O. Technically, as you're probably aware if you look in a data booklet, we could have a look at an ester because it will have a different peak at CO, which an aldehyde and ketone won't contain, but we're not going to talk about that in this video. Okay, so next question. I'd like you to have a go at answering this since I've answered this one. So can we identify between a carboxylic acid and a ketone and an aldehyde? Okay, give you a minute to think about it. Okay, so can we identify it? I reckon yes we can, and you've probably worked this out as well. So yes. Why? Because in a carboxylic acid, there will be a very broad peak at about 3,300 centimeters -1, which shows an OH. Okay, I'm just writing 3,300. You can quote whatever is in your data booklet. Right, and a ketone and aldehyde, well, we know from their functional group that they don't have a hydroxy group or an OH group. Therefore, the aldehyde and ketone spectrum will not have this peak. Okay, pretty self-explanatory, yeah? So we can label these. This is my example. This is my spectrum of 2-hydroxypropanoic acid. So we've got an OH, we've got 2 OH groups in fact, but really we're looking at this carboxylic acid group here. So this is my OH, and this is the sharp peak at 1740. So this is C double bond O. And I've talked about the CH as well. Well, what actually happens in a carboxylic acid is that the CH peak is round about here. You can see as I'm drawing, yeah? So it's been incorporated into the very broad OH peak of the carboxylic acid. But the main thing to take away is that a carboxylic acid will have a C double bond O peak and an OH peak. Therefore, we can tell the difference between carboxylic acids, aldehydes, and ketones. Okay, so moving on. Uses of infrared spectroscopy. So we use them in modern breathalyzers. To measure ethanol levels. And we'll do one more. And for drug analysis. Okay, so moving on to mass spectrometry. Okay, so mass spectrometry. So mass spectrometry can be used to find isotopic abundance of isotopes of an element, and relative atomic masses can be calculated, using the following formula. We're not going to spend too long on this because I have another video on it. So this means the sum of the percentage abundance of isotope times by the AR of isotope, and if it's a percentage we divide by 100. It can also be used to determine the structure of an organic molecule from molecular ion peaks and fragmentation patterns. We'll come on to talk about them in a little bit. Okay, so determine the AR and identify the element below from the data provided. I'll later have a go at this, and I'll give you a couple of minutes to answer the question. Okay, so I'm sure you've worked out this question. So the first thing we need to do is work out the percentage abundance of my AR of 24, my AR isotope of 24. So I can do that by using 100 minus 12.7 plus 13.9 gives me a percentage abundance of 73.4. Now I can use this formula, so percentage abundance of isotope times by the AR of isotope, and then add them all together. So 73.4 times by 24 plus 12.7 times by 25 and 13.9 times by 26. Because it's a percentage divided by 100, which gives me a value of, it doesn't give me a value of 24.2, it gives me a value of 24.4. Therefore, we look on the periodic table, and the thing which is closest to this value is magnesium. Okay, so moving on. So determining structures from mass spectra of organic molecules. So it's difficult to determine a complete structure from mass spectra alone. Usually is combined with another technique, such as infrared spectroscopy. Determining parts of a structure involves looking at fragmentation patterns. Okay, So when a vaporized sample of an unknown chemical is passed through a mass spectrometer, one electron will be knocked off to produce the positive ion of the molecule. This will have the same MR of the original molecule. Okay, so give you a minute to think about it. Okay, and I'm sure you've managed to work it out. So why will it have the same MR? Well, because electron mass is negligible. So we haven't lost any protons, we haven't lost any neutrons, so it's still going to have the same MR. So if I was going to have my molecule, I pass it into a mass spectrometer. I still have my molecule, but I've knocked off one electron. So this MR and this MR will be the same. And this is important. Okay, so what do we call this? So this is called the molecular ion peak, and is found to the furthest right of the spectrum. And I'm just going to change this to usually. You may see a tiny little peak which is further to the right than the molecular ion peak. Don't worry about that. That's to do with the carbon-13 isotope. So if you see one of them, if you're looking for the molecular ion peak, it will be the big peak which is furthest to the right of a spectrum. Okay, so I'd like to have a go at answering this question. So what would be the molecular ion peak of propanal and propanone? So when I say what would be, I mean what would be the value. Okay, so I'm sure you've worked this out, that my molecular formula of propanal and propanone would be C3H6O. Because it's an ion, I need to put a positive charge, and I add all these up and it would equal 58. Right, so we cannot identify an organic molecule precisely from just the molecular ion peak. To identify it further, we must look at fragmentation ions or fragmentation patterns. So fragmentation ions occur due to the organic molecule being bombarded with electrons in the mass spectrometer. It means the organic molecule will break up into smaller pieces, e.g., and I'll do an example. And just as a quick point, it doesn't mean that we're only putting one molecule into a mass spectrometer. What we're doing is putting lots of molecules of the same molecule into the mass spectrometer, so it can break up in lots and lots of different ways. Okay, so what do I mean? So if I draw propanone and propanal, so this would be propanal, and just as a bit of practice you can have a go at doing propanone yourself. Okay, I'm sure you've drawn something like this. You may have drawn a displayed formula, that's absolutely fine. Okay, so I have my propanal and I have my propanone. So this can break up, or these molecules can break up in lots of different ways. However, I'm going to say that one way it can break up in propanal is it's going to break here. In propanone, I'm going to say it breaks here. So now, that means if this breaks up, I'm going to have one positive ion produced. So I am going to produce here CH3, CH2, CHO is broken up to produce CH3, CH2 positive plus CHO. And here I'm going to have CH3, CO, CH3 as broken up to produce CH3 and CO positive plus CH. Okay, so if I look at my MZ values of my CH3, CH2 and add them up, I am going to get a value of 29. Here, if I add up my CH3 and CO plus, I'm going to get an MZ value of 43. Now, if I had a mass spectrometer, actually, I'll stop there. What I'd like you to do now is to sketch the resultant mass spectrums of propanal and propanone and label the important features. Okay, so think about what types of fragment ions you may get for these two molecules. Okay, so I have to go at sketching them. I haven't drawn all of the fragmentation ions on it. I've just drawn the important ones. You'll see that two are labelled as green. Right, so the furthest one to the right is going to be my molecular ion peak. And that's going to be at the same value for propanal and propanone. As we worked out, it must be at 58. So this value, this value would be 58, this value would be 58, and this peak would represent C3H6O, don't forget the plus, C3H6O plus. I also have a value at 15 and a value 15. I'm sure you've worked it out. This would be CH3 plus, and this would be CH3 plus. However, we have two different values. So I have one at 29 on my propanal, and I have one at 43 on my propanone. Now these can only occur if they are these two types of molecules. So here I would have a value of CH3CH2 plus at 29 for propanal. So this represents CH3CH2 plus. I cannot get this peak in propanone because I don't have any CH2s. And in propanone I would have a peak at CH3 at 43, which would represent CH3CO plus, and I cannot get this peak at in propanal either. Therefore, we have two identifying peaks that can identify the organic molecule in question. Just as a side note, 29 would also equal 12 plus 16 plus 1, just make sure I've added up. It could also represent the COH plus, but this isn't as likely. It's more likely to represent CH2, but again, still can't have it in propanone. So I can identify the structure from my mass spectrum data. Okay, so moving on. So the fingerprint region. So the fingerprint region is below 1000 centimeters to the minus 1. Each molecule, or every molecule, has a specific fingerprint region therefore can be identified using a database. So unsurprisingly, the fingerprint region is very much like your own fingerprints. So every single molecule will have a characteristic fingerprint region that we can use to identify the molecule. However, you won't be able to use it in an exam because you're not showing any knowledge. Okay, so moving on. So combining techniques together. So often some analytical techniques are combined together for longer answer questions in the exam. You'll be asked to identify an unknown organic compound using the information provided. It can be difficult to get all the marks when answering these questions, even if you chose the right molecule. Things to remember. So there are 3 points. First one. Identify each functional group via infrared spectroscopy. To identify the molecular ion peak, and sometimes it's 1, but I'd always say 2. Identify at least 2 fragmentation ions. Okay, so even if you've worked out what the organic molecule is, you need to make it explicitly clear to the examiner that you have used all the information so they can give you the marks. Okay, so we'll have a quick go at doing a question and then we're done. So I'll quickly read the question. So butanoic acid, 2-methylpropan-2-ol and butanol can be identified via infrared and mass spectrometry. Describe how this could be carried out and sketch any relevant spectrums and details. Okay, I'll give you probably 10 minutes to do this. Okay, so let's go through the answer. So I can identify butanoic acid from an infrared spectrum. So butanoic acid will have a very sharp peak at 1740 centimeters -1, C double bond O. Butanol and 2-methylpropan-2-ol will not, because they do not contain a C double bond O. So I've sketched it here. So they will all have the OH, but I still have to draw it on. But the actual peak that we want to look at is C double bond O. So there will be a sharp absorbance or peak at 1740 centimeters -1 in butanoic acid, but not in butanol or 2-methylpropan-2-ol. Okay, so moving on. So 2-methylpropan-2-ol and butanol can be identified from mass spectrometry. So I've drawn the structures out. Now they both will have a molecular ion peak at 74 and 74. So both have a molecular ion peak at 74. Remember, don't forget to put your positive on. However, 2-methylpropan-2-ol will have a peak at 42, which would be my CH3 positive, and butanol will have a peak at 39, which is CH2 positive. These peaks can only occur in these specific structures. So I would be breaking it here, and I would be breaking it here. Okay, there are lots of other different fragment ion peaks that you can put on, or you might be asked to identify. I've just put on a 15 and 15 on both of them. Okay, so quite quick. Hope that was useful, and there is another video which goes on to more analytical techniques. So this is really the introductory video, but as I said, I hope you found that useful, and I will see you next time. Okay, bye bye.